Figure 2 shows a sketch of part of the graph y is equal to f of x, where f of x is 2 lots of the modulus of 3 minus x plus 5, where x is greater than or equal to 0. State the range of f. Okay, so to state the range of f, we have to know what this point here is. To work out this point, we have to think about the transformations that have happened to a modulus x graph to make it what we have over here. Okay, so modulus x graph looks like this. The lowest point there is 0, 0. Before we proceed to the first transformation, let's rewrite what we have over here. So our f of x, we can rewrite that as 2 lots of the modulus of, instead of 3 minus x, we can write that as x minus 3. We can basically times that entire inside by minus 1. Why are we allowed to do that, and why are we doing it in the first place? Well, if we think about, let's say, modulus of minus 5, this is no different to the modulus of 5, because the modulus symbol gets rid of minus signs. It gives you the magnitude of something, it doesn't give you a minus sign when you use it. So both of these two things are equivalent, they're both just equal to 5. So then if we were to multiply the inside of a modulus function by minus 1, we just get the exact same thing that we had before. So modulus of x minus 3 is no different to modulus of 3 minus x. But why is that useful? It's useful because it's a bit easier to see what the transformation will be when going from modulus x to this. Alright, so let's discuss those transformations now. First transformation is this minus 3 over here. That affects the x values and it moves the entire graph to the right by 3 places. So the new graph will look like this, where this is 3, 0. Next transformation is this 2. That affects the y coordinates. It's not affecting the x values as it's outside the modulus symbol. We're multiplying all the y coordinates by 2. That stretches the entire thing vertically, scale factor 2, parallel to the y-axis. This coordinate here will still be 3, 0, because the y coordinate of 0, when you times it by 2, remains the same. And then the final transformation, this plus 5, again affects the y coordinates as it's outside the modulus symbol. The whole graph moves up by 5 places. So now the graph will look like this, where this is 3, 5. So then going back to the diagram that we have over here, this point here must be 3, 5. And that will help us work out what the range of this function is, because this is the lowest point of our modulus function. The range is the output y values. We can see from the graph now that the lowest y value is 5, and the highest y value is infinite. This graph just continuously goes on to infinity. It stops here because of the domain of x is greater than or equal to 0. This portion of the graph goes on to positive infinity. Therefore, our range of f of x will be f of x is greater than or equal to 5. So that's part A. On to part B. Solve the equation f of x is equal to a half x plus 30. So one thing to bear in mind for this question is that we are not redefining what f of x is. F of x is defined over here. F of x is set to be equal to 2 lots of this stuff. What's happening here is this f of x is used as a placeholder for this function over here. So this is basically saying 2 lots of the modulus of 3 minus x plus 5, or f of x. So this thing here is equal to a half x plus 30. So that's what that equation is saying. Let's just write that down. I'll use the x minus 3 form that we had before. So this plus 5, that's our f of x, what we have over here, and that's equal to a half x plus 30. So this is what we're solving. And to solve this, the way that Edexcel likes you to do it is to sketch the graph. So let's do it that way. To do that, we have to know the y-intercept for this line over here so we can place this line relative to it. So I'll back up a step. What we're doing is sketching this function on the same graph as this one, and then seeing where the two things intersect. Where the two things intersect is the solution to this equation. Right, so going back to the modulus function, we want to know what the y-intercept is over here. To do that, we have to work out the equation of this line. We can figure that out from this modulus function. So the equations of these two lines here and here will be 2 lots of positive x minus 3 plus 5, that will be one of them. And the other one would be 2 lots of negative x minus 3. Negative of that would be 3 minus x plus 5. So I've basically just made this thing positive and negative, so kept it as is, times the whole thing by -1. Because these two are not inside the modulus symbol, they just stay the same. These will be the equations for the two lines of the modulus function. I'll just expand those out. So y is equal to 2x, that'd be -6 plus 5, which would be -1. And this one will be -2x plus 6 plus 5, which would be plus 11. Right? So then one of them has a negative gradient, one of them has a positive gradient. So then this one must be the line which has a negative gradient. That was y is equal to -2x plus 11. And the other one was 2x minus 1. Okay, so now we have the equations of those two lines. Next step, work out the y-intercept for the left-hand side line. Well, we can see from the equation that we have over here that y-intercept will be 0, 11. I'll just write 11 next to that. And now we can sketch this line over here, the half x plus 30. So half x plus 30, the y-intercept is 30, so it's above the 11. This is not to scale at all, but I'll just put it over here as it makes sketching the diagram a little bit easier. And looking at the gradient of this line, it's a half x plus 30. The gradient is a half, and that is less than the gradient of this line over here. So the line I'm about to draw has a gradient of a half. That's less than the gradient of this line, and therefore it will be shallower than this line. So it'll look something like this, not to scale at all again. These two lines will cross at some point, and what this diagram has told us is that this line of y is equal to a half x plus 30 intersects only with this line and not with this one. So that's the reason we did this whole process. Alright, so then we equate these two or solve these two things simultaneously. Half x plus 30 is equal to 2x minus 1. 2x minus a half x is 3 over 2x. Bring the 1 over, we get 31. This is equal to 31, times that by 2 over 3, and we end up with 62 over 3, which is our final answer for part B. On to part C. Right, so it says, given that the equation f of x is equal to k, where k is a constant, has two distinct roots, state the set of possible values of k. Okay, so f of x is equal to k. Again, f of x is this function over here. So if we're setting f of x to be equal to k, that means we're basically solving the equations y is equal to f of x, which is the modulus function, and y is equal to k simultaneously. If we're solving these two equations simultaneously, then we'll end up with f of x is equal to k. That's just equating them for y. That is the equation, f of x equal to k is the equation that we have over here. So that's what we're solving. If we're solving these two equations simultaneously, then we're looking to see where they cross on the graph, where they intersect on the graph. Y is equal to k is just a horizontal line with y-intercept k. And then we're trying to see what k values will give us two distinct roots to this equation. In other words, what k values would mean that this graph crosses this one in two places. So let's draw that on our graph. We can get rid of some of this stuff that we had from before. We don't need it anymore. Okay, so I've just left the important information that we need for this question. I'm just going to draw a horizontal line now. So there is my horizontal line. I'm just going to grab that. This is my y is equal to k. So the y-intercept of this horizontal line varies. It's equal to k. That's an unknown quantity. So this thing is just going up and down, and we're trying to see what positions of k would it have such that it crosses this modulus function twice. So as we can see, it crosses once. We get to this point over here, it starts to cross twice, and then beneath this point, it stops hitting the modulus function. So then we're thinking about this interval from here to here. K, which is the y-intercept of this line, k has to be less than or equal to 11, and it has to be greater than 5, not equal to 5. If it were equal to 5, there's only one solution. There's only one place where this line crosses the modulus function. So it has to be greater than 5 to have two solutions, and less than or equal to 11. So that is our interval. K is more than 5, less than or equal to 11. And then we want it in set notation as well. So K colon put 1 squiggly over here, 1 there. That is our final answer.